Hi everybody. Okay, we're here and we're ready for our last example. This is example 3 in our session 12, polynomial and rational inequalities. And the example is this one. It's on the left-hand side. It's a rational function, so x squared minus 5x plus 6 over x squared minus 5x. And then that is greater than or equal to 0. So we're trying to figure out what are all the different numbers we could plug in for x that will make this left-hand side. A will give us an answer instead of being undefined, and B will give us an answer that is either bigger than or equal to 0. So the idea that we're going to use here is quite similar to the idea that we used before, but with one more thing to be aware of. So in order to point that out, I'm going to show you the graph. That will sort of give away the answer in a certain sense, but the key is how are we going to work with the algebra, with the equation, or with the inequality to find the same answers that we can see in the graph. So this is a graph of this thing, and you can see that the graph consists of, it looks like 3 pieces. There's a piece here, there's a vertical asymptote, there's a piece here, there's another vertical asymptote, and then there's a piece here. And we're looking along the x-axis, what are the different x's that we can choose that when we plug that x into the function and we get an answer, it gives us an answer that is bigger than or equal to 0. So that's what we're after. Now, if you think about moving along the function from the left side, here it's entirely above the x-axis. The x-axis is here and the graph lies above, which means that any number you plug in for x here is going to give you an answer, an output answer of something positive, something bigger than 0. So these are all numbers for x that should be included. And they go sort of from negative infinity all the way up until they reach this asymptote. Now, at the asymptote, it's undefined, so we're not going to include that asymptote itself. That asymptote looks like it's right on the y-axis. And that corresponds to the point where x is 0. So where x is 0, this function seems to be undefined. It's at an asymptote there. And then it switches to being negative. And that's the important part here, is that somehow we've managed to switch from a positive part of the function to a negative part of the function without actually crossing the x-axis in the middle. And that's something that we need to worry about in rational functions. They can have this behavior, whereas polynomial functions can't. And the difference is to do with the asymptotes. These asymptotes, the places where the function is not defined, are places where it can jump from being positive to being negative without ever crossing the x-axis. So if we're trying to think about where are the dividing lines between positive and negative parts, there's a positive part of the function here, and a negative part of the function here, and the dividing line between them is not a place where it crosses the x-axis, but a place where the function has an asymptote or is undefined. Similarly, if we look on this side, here there's a positive part, and here there's a negative part, and if we try to get from one to the other, you'll see that we cross this asymptote. So that's almost all of the places we have to worry about. Here, it looks a little bit like the graph maybe just touches the x-axis without crossing it. But if we zoom in a bit, you can see from the graph here that this really makes it seem like it actually crosses the x-axis there and again there. And that means that there might be a little part in here where that graph is above the x-axis, where it's bigger than 0, which means that we would want to include that little part in the middle also. And this little part, you'll notice, is bordered by places where it actually crosses the x-axis. So when I look at this graph, I see 4 different places that are going to be important to us. And those 4 places are, let's see. They're the place where the vertical asymptote is here and here, and the places where it crosses the x-axis here and here. So there's sort of 4 points that we need to worry about here. And once we have those 4 points, we've divided the whole number line up into intervals. And on each interval, it's either entirely above or entirely below the x-axis. Here it's above, here it's below, here it's above. Okay. I happen to know ahead of time that this is above right here, but if not, don't worry. When we do the algebra, you will see that it works out, that we find that spot, we detect that spot. Okay, so here's what we're going to do. we need to find first these 4 places. And to find those 4 places, that now takes 2 steps instead of 1. So the way that we're going to do it is we're going to say step 1. We're going to find the places where it's equal to 0. And to do that, we only have to worry about the numerators. So we set the numerator equal to 0 and solve. That'll give us the places where it actually hits the x-axis. And then sort of step 2, in finding these points, we're going to set the denominator equal to 0. And solve. And that will give us the places where it's undefined. That'll help us find where those asymptotes are. And if we find all of the values here, we're going to use all of the values in step 1 and step 2 to break up our number line into chunks, into intervals. And then we're going to do, just as we did above, we're going to test each interval by picking a point in it and seeing whether the function is positive there or negative there. Okay? So here's the steps 1 and 2, and in this case it's luckily not so bad. So step 1, we set the numerator equal to 0, x squared minus 5x plus 6, set it equal to 0, and to solve this, well, we can factor this one. So we need 2 numbers that multiply to give positive 6 and add up to negative 5, and negative 2 and negative 3 work. Double check that for yourself. And this ends up giving you 2 solutions. If x minus 2 is 0, then x is equal to 2. And if x minus 3 is 0, then x is equal to 3. So these are zeros of the function. The zeros are like the places where it crosses the x-axis. And if we look at the graph, you can see that here's x equals 0, x equal, let me see, 1, 2, 3, 4, 5. It looks like x equal 2 and x equal 3. Those are just the places that we found, 2 and 3. And those are the only places where the graph, the blue part of the graph, actually touches the x-axis. Okay, so now let's go to step 2. We'll jump down below the graph in order to do this. Here. Step 2 is set the denominator equal to 0, and the denominator is x squared minus 5x equal 0. When the denominator is 0, we're going to get something that's undefined because we can't have 0 on the bottom. We can't divide by 0. And so setting denominator equal to 0 is going to tell us what are the places where the graph is undefined, where the function is undefined. To solve this, x squared minus 5x equals 0, this one you'll notice that both of the terms here have an x in them. So we can actually factor this by just factoring out an x. It's x times x minus 5 equals 0. And then once again, we can set each thing equal to 0. The x equals 0 and the x minus 5 equals 0. X equals 0 just gives us an answer, and x minus 5, if we add 5, we get that x is 5. Okay. So these are places where the function is undefined. Now, imagining that we didn't have this graph to look at, what we would do at this point is we would say, okay, we found places where the graph crosses the x-axis or touches the x-axis, the zeros, and we found the places where it's undefined. That means it could have asymptotes and so on. Let's just make a number line for the x-axis. And on this number line, let's put in all of those numbers. And the numbers that we found were, well, let me see. 0 was one of them. That was one of the places that was undefined. And, you know, since it's undefined there, undefined means we're not going to be including that number in any of our solutions, because our solution, we only want places where it's defined. Here, let's see if I can fix it that way. There we go. So instead of putting a solid dot there, I'm going to put an open dot there. And that open dot is going to be really helpful to us later. It's going to let us know that this is a place where the function is not positive, it's not negative, it's undefined. So that was at x equals 0. And there's another one down here at x equals 5. I'm going to put an open dot there as well. Now, there were also two places, if we scroll up, 2 and 3, x equal 2 and x equal 3, where the function was equal to 0. And so we put in, let me see, 1, 2, 3, 4. Here's 2 and 3. And you'll notice that on 2 and 3, I'm going to put closed dots, because on those points, it actually equals 0. It hits the x-axis. Okay. And now what do? Well, we have a bunch of intervals here. We have the interval, everything to the left of 0. We have everything between 0 and 2, everything between 2 and 3, everything between 3 and 5, and everything above 5. And all of this, that's 1, 2, 3, 4, 5 intervals. What are we going to do? We're going to test each one of those intervals and determine whether the original function, the entire fraction, is positive or negative there. Let's make a copy of this thing and bring it down below where we can see it. So this guy, this is our function. And I guess we want to know when is it bigger than 0. That's the overall goal. Okay, so now it's just a bunch of testing. To test this guy, let's see. What we want to do is, in each one of the intervals on our number line, we're going to pick a number, not one of the endpoints, but another number, and we're going to plug it into our original function, that entire fraction, x squared minus 5x plus 6 over x squared minus 5x. If you want to pause the video and go ahead and do that now, go for it. When you come back, I'll go ahead and go through it as well, so you can follow me if that's helpful. Okay. The first interval I'm going to test is the one here on the left, and I'm just going to pick any number down here. I could pick the number -1 or -2 or -3 or -4. I'm going to choose -1 just because it's easy. And if we test x equal -1, well, we plug it into our function, and our function is x squared, so that's -1 squared, minus 5 times -1 plus 6. And on the bottom, we have -1 squared minus 5 times -1. And altogether, what does this give us? This one I'll calculate, although in the future I'm going to rely on a calculator to do it. So the -1 squared gives us 1. Minus 5 times -1 gives us plus 5 and plus 6. And on the bottom, we have 1 plus 5. So this looks like it's going to be 12 over 6, which is positive 2. Positive 2 is bigger than 0. That was an accident. That one is bigger than 0. And because of that, we're going to mark this interval with a plus. So everything from x equals 0 to the left, that function is positive. That corresponds in the picture. Here's x equals 0, and this is everything to the left. You can see that the function lies entirely above the x-axis. And you can imagine if we did not have access to this picture when we were solving this problem, that's how we could tell that that's the part of the function that's above the x-axis. So this is going to be included in our solution since we want things that are places where the function is bigger than 0. Okay, let's test each of the other intervals. So the next interval goes between 0 and 2. I'm going to choose the point 1, just right in between them. So testing x equal 1. Well, what is it? It's 1 squared minus 5 times 1 plus 6 over 1 squared minus 5 times 1. And if we plug those guys in, then we get, here we go, negative 0.5. So that's negative in there. This guy is negative. Now, let's look at the interval between 2 and 3. And between 2 and 3, we're going to have to, there's no nice whole numbers in there. We're just going to have to choose a fraction. Let's choose the number 2.5, which is the same as 5 halves. So x equals 5 halves. This one, when we plug it in, it looks messy. It's 5 halves squared minus 5 times 5 halves plus 6 over 5 halves squared minus 5 times 5 halves. And here I'm going to ask the calculator to do it for me. When I plug that thing in, I get 0.04, and in particular, it's positive 0.04. And that means that that little interval, the function is positive on that little interval between 2 and 3. That corresponds in the picture to this little part of the function here, and it says that it is positive. It's above the x-axis there, although it's a little bit hard to tell when you're zoomed out, especially. Okay, let's keep going. If we test x equal 4, we get an output of the function of negative 0.5. So it's negative in that interval between 3 and 5. And then above 5 if we choose x equals 6 and put it in. For that one, if we plug in, we get a positive 2. And that one's bigger than 0, so that's positive. Now, we're interested for this problem in including all of the places where this function is bigger than 0, not equal to, but bigger than. And that means we're going to include all of the numbers down here, up to, but not including 0. We're going to include the numbers between 2 and 3, but not including 2 or 3. And we're going to include the numbers above 5. So our solution goes, whoopsie. Hey, there we go. So our solution goes, answer. It goes from minus infinity to 0, and I'm putting a round bracket because that 0 is not included. It's not included. It wouldn't matter whether it said greater than or equal to or just greater than. It wouldn't be included in either case because here the function is undefined. The next one we're going to include is between 2 and 3. And then lastly, we're going to include from 5 to infinity. Okay, that's our answer. And a good challenge is to start this problem yourself and see if you can work through it without referring to the graph and see if you can come up with this. All right, great work, you guys. Give these problems a try on the web work, and feel free to ask me if you have questions or problems.